Greetings, gentle readers. April 2, 2026. Reading Foundations today. I've been recording video essays, rather like these, for 3 or 4 years now, about three years now, in a month or so. And so that's been personally kind of cultivating a practice in the extemporized, spontaneous accounts of the study of foundations, as it's put, or in continuity infinity as primary. And it's been also a chance for the second course of a sort of sort of a directed self-study of differential equations in this kind of account, leading to the great recourse to integral equations, the complement that's so often missing and left to the edges beyond the partial, about the fact that in something like axiomatic set theories, account of descriptive set theory, relating to theories of objects of mathematics, of this domain of discourse, the universe of the objects of mathematics, that the realities and regularities of well-foundedness, well-ordering, and well-dispersion are then found to make for deconstructive accounts of arithmetic. As for geometry and number theory, for arithmetizations, algebraizations, and geometrizations, and then as for number theory and topology, is the flexing of the accounts, if not so much flexible, and being very well defined and coherent, meaning having one definition to things. And for the operator theory is basically the account of any kind of calculus at all, which is usually understood as real analysis's account, or infinitesimal analysis's account, as it may be, of the mensuration, that word meaning to make measures of things. That then the deconstructive account of arithmetic, for example, is separated from the usual attachment to the Galois groups in abstract algebra, which, while it still has, that it's a bit more fundamental to have the increment and the partition before addition and division, and the account of long subtraction, as is put here, making for so why then it can kind of meet in the middle of what otherwise these two inductive accounts intending to attain towards each other, but contradicted by the fact that they cannot complete each other, except in this wider, fuller dialectic of the deductive account. That's kind of a little bit more firmly established, at least in written, spoken words, vis-a-vis the written words, where these have been quite thoroughly expounded upon for decades, more like 3 decades than 3 years, in the tens of thousands of essays to Usenet, many brief and some even useless in the accounts of the trappings of trolls and such unmoderated, open, voluntary foray on the entire internet, compared to the longer essays and the formalizations and the developments, where generally in my courses I just write what I'm working on, no matter what anybody's saying, and so I'll just follow along the thread and just keep piling on the thread. And then the way it works out is I can just cut exactly and only what I say, and it's a self-contained account that it makes all these mathematics very well explored and well explained, and in some few cases discoveries. And then, of course, is a historiographic account, because it doesn't make much sense to leave behind the history which made for all these sorts of developments. I have a mathematics degree, including the usual accounts for physics or science and biology, the mechanics and electricity and magnetism as for the mechanical account, the electrical account. And then for general relativity and quantum theory, I've sat the standard linear curriculum and passed it, I guess you might say. And then for a mathematics degree, the usual standard linear narrative and the standard account. I got a really high score on the SAT and the GRE, and 99 to 95% at least. So I mean, according to at least some of those measures, I felt like I was pretty lucky in school, because I had about zero homework, and somehow it all got done. So that's just to say it. It's got the skills and the credentials with regards to then this kind of historiographic account, but most particularly so because of all the work. So that's the way to then look at in kind of a retrospective of these kinds of video essays, that it's to help establish some credence, and that these are usual accounts of for our ideal ivory tower, which is this canon and dogma and doctrine, our candidate for foundations. And besides that, primary research and development is a macroscopic input to the great formula that makes the gross domestic product, has that. It always, since 80 years ago, has correlated with real growth, the investment in research and development, then that the applications so follow is profound. And that then this is an account of the big science. Getting back into the box of books then, where we left off is I took Hermann Weyl's Levels of Infinity and tossed it back on the stack. And then I drew back also this Fritz London's account of the superfluidity, macroscopic theories of superconductivity, because it's deemed kind of relevant. So the previous talk was about continuous quanta, and the talk before that was double relativity. So continuous quanta is basically to take for the account of quantum mechanics, how it's a continuum mechanics again. And so that is related to many matters of the discoveries since the atomic age at all. After the accounts of the measurement of the electron, its charge to mass ratio. It's never quite just charge or mass by itself, but the charge to mass ratio. And then the accounts of the equivalency of energy. Here's it's put the E equivalency of energy is for Einstein, that being a great sort of account, and really why the annus mirabilis was putting these things together, as that belongs to Planck, and as that belongs to Lorentz and Neumann, Henrik Anton Lorentz and Carl Neumann, for example, and as in all the electrical stuff belongs to, beyond Maxwell, Fitzgerald and Heaviside and Larmor, Faraday, besides Ampere and Coulomb and the like. Each one of these then getting into descriptions that then for things like Rutherford and the nuclear theories, then as to be what's making for, after this E equivalency of energy, the forces and fields, the F Lorentzians, those basically describing anything in time according to a theory of at least some relativity of motion in the usual account. And then for double relativity of motion in space, otherwise those being absolutes, that it's just a computational setting, it's just a mathematical setting to write the expressions for these expressions and relations is what make it so that's deemed a rather thorough sort of account. So that said, then I'll get into some books here. Fritz London's Superfluids, Hermann Weyl's Levels of Infinity. So the infinity is kind of, its analytical account is after things like Cavalieri and the indivisibles, which is the account otherwise of the eudoxus and the eudoxon since the time of Aristotle at least, with regards to the Archimedean field. There's infinitely many, there's no infinitely grand, it's an Archimedean field. It's infinitely divisible. They're members of first the ordered field, the rationals, and secondly the complete ordered field, the reals in this account. And then for you, Dedekind as way after that, and not saying much and just being a reductionist, that I kind of would omit Dedekind from really saying anything. Instead, there's Cauchy and Weierstrass, and they give the great account of delta-epsilonics, say, and those being the stack of derivations that makes for the intermediate value theorem, that the fundamental theorem of the derivative and the fundamental theorem of the integral are so given. About the brief accounts with the vanishing difference, and whether or not that's dividing by 0 to leave that be in its account, because it just gets related to the geometric series to make a prototype of the measurable. And then as with regards to the tangent as the derivative and this sort of account, that it's related to the theory of the curves, the functions, as the classical functions in these sorts of means, then with the usual attachment directly to the Cartesian, that to the Euclidean. This is considered the old hat, meaning it's de rigueur, it's completely standard, it's the standard linear narrative of the standard linear curriculum. Great. So Cavalieri was with infinitesimals. He's like, well, we got everything is infinitely divisible, but what about indivisibles? And so that's just kind of relation to that. So in the time of Galileo, before there was Cavalieri, and so it's associated with him, this account of why that's so. And then reading from Price in the infinitesimal calculus the other day, this is a textbook from 1850, which basically describes that it is about these the infinitesimals, as they would so be, because they're not just differences. Finite differences are infinitely divisible. Because the perfect results of the calculus only arrive as from the differential, and somehow less than that. And then to keep that from being a paradoxical contradiction is these three accounts of continuous domains: line reals, field reals, signal reals, and then that as with regards to those being different models in this axiomatic set theory, then in the descriptive set theory, which is saying, okay, we're going to make definitions and say these things as sets, all the relations they so structure as they model, and superimpose a piece are these definitions of the objects of mathematics. There's at least three continuous domains of as sets, and all their relations also as sets and sets and sets and ad infinitum in a set theory, a theory of one relation, or any other equi-interpretable theory which would purport to be fundamental, like ordering theory or partition theory, or class set distinction, making class theory, and then sets is, fictitious of those. Any other theory of one relation, or various accounts of type theory or category theory as being equi-interpretable, suffering the same problems, if not having exactly the same baggage, where usual accounts of today would be like, let's leave behind all the baggage and just imagine we're perfect. It's like, well, somebody already did that, and doing it that way is not. So these kinds of things are like so. And that model theory and proof theory are kind of deemed equi-interpretable too. A proof is as simple as this is so, that is so, implies that if that is not so, then this is not so. The contrapositive is a proof, but the entire model theory of all the relations, then what keeps that equi-interpretable isn't the same thing as saying one is the same as the other, the briefest way you can write it, but it's just so that no matter how you write it, they end up being the same. That's one theory in this kind of thing. But then the levels of infinity got it to basically the duBois-Reymond. And I'll often confuse Paul and Emile, duBois-Reymond, or father and son. And because Paul was a researcher in infinity, and then Emile was more of a biologist, if I'm not mistaken, but as well prominent and novel in his field. So that just makes an account for then. And then Jorg Cantor, came to be promontory and considered novel, although a lot of his results are just kind of, they were already around. For example, the anti-diagonal result was first written by duBois-Reymond or something like that. That then the attachment to the Mengen-Layer, the set theory, writing the descriptive account in the axiomatic set theory's account. And then for things like, well, what about Gottlob Frege, or Frege, I'll often say, or then as for Russell and the account of Russell's retro thesis and all that kind of stuff here. The paradoxes are also resolved here as by this account of what's called sweep in principle. It kind of sweeps these slates, the slates of uncountability and the slates of paradox, mathematical and logical paradox, so as to arrive at that they're resolved instead of contradicting each other. which anybody can readily demonstrate they otherwise do. And then there's this account of how that came to be our enshrined as our modern mathematics is that after the Pythagorean, everything is rational, or almost everything is rational. And that's most people's best, most faithful understanding of mathematics, because it's rational. And then in the in Cantorian account, it's that, well, actually almost all or everything is transcendental, meaning it's beyond the rational. And it's like, well, that's great, because it eventually just gives an otherwise inconclusive account of a difference between the natural numbers, their cardinal as a set, and the real numbers, their cardinal sets. You can say anything that's less than that, after that strict sort of inequality, it's got measure 0. So, and on the one hand makes a lot of stuff simpler later to talk about points in the world of lines and points in measures, because the one hand it's just it can never be without so drawing the line, as it were, and as it is here, the line drawing. That then here, instead of the account of measure 0 and for the almost everywhere, and these sorts of things being compromises, because otherwise Jordan measure and Jordan content as line reals, and Dirichlet and those sorts of metrizing ultrafilters as signal reals don't meet and indeed contradict by their very existence. Otherwise, the Archimedean field, the field reals, besides things like non-Archimedean fields, the infinite, the hyper reals, or Conway's surreal numbers, these are more measurable things. To make for Vitali, the mathematician who gave an account of what then the set theorists had to call a non-measurable set, when really it's just an example of the doubling space and doubling measure, halving space and halving measure. And it's about the pi ratio space. These, along with something like the geometric series, the half and half and half again, that sum to 1 for Zeno's arguments, that Vitali and then Hausdorff are considered the great geometers, giving the measure theoretic account of the quasi-invariant or the non-standard measure theory, which is real. It has real analytical character. So then many accounts try to build on that. And the problem is it's not really made for an extension. And so there are many accounts that are like, well, this is a conservative extension of ZFC, Zermelo-Fraenkel set theory with the axiom of choice. Or this is a conservative extension of ZF set theory. And why is because then it doesn't actually prove any contradictions, because otherwise to actually add anything onto that, it would prove contradictions. And there's many accounts of mathematics wrestling with that itself, because it didn't take the deconstructive account first and just arrive as like, well, in our theory of functions we have the one that's non-Cartesian, it's sweep, or it's a natural unit equivalency function. It is. So that is mathematical, it's geometrical, and it relates to number theory. Then so that's why it's been kind of how one might say unable to make progress. Otherwise, in these accounts of the great atlas of independence, as contra the giant monster of independence, as Erdős put it, because Erdős, in his accounts of past Ramsey theory and into infinite progressions and numbers and stuff like that, found contradictions. And then you frame them as conjectures because he'd prove them both ways, and then say, well, I guess it's open. But really, this giant monster of independence then is you get resolved that just like there's these 3 models of continuous domains and 3 models of Cantor spaces, there's 3 laws of large numbers, and then for all kinds of related results in convergence and emergence, because there are plenty of expressions that, according to many laws of convergence, fast and slow, fail. And so this great atlas of mathematical independence is after this sort of deconstructive account, and it's the only sort of way to make it so instead of adding on top of the axioms of set theory for axiomatic set theory and descriptive set theory, to get underneath that. And then as well, the standard accounts that they give these standard infinitesimals, the iota values, the line reals, or contradictions, like as for why well ordering, well dispersion, and well foundedness are each rulal and regular, and contradict each other. those can be made readily, standardly, anyways. And so any kind of formal account, like the modern theorem provers of the day, the language of the inference machines, that can be written quite directly, just as easily as it's put here in natural language. So it's all one theory. Otherwise, it's not. So, and it's figured that mathematics is all one theory, and there is one, and it's discovered, not invented. That being the usual idea. So fundamentals. Here's a quote from on David Hilbert in his mathematical work from Hermann Weyl. He says, Hilbert was not willing to make the heavy sacrifices which Brouwer's standpoint demanded, and he saw at least an outline, a way by which the cruel mutilation could be avoided. So Hilbert is got his account of geometry, and he gives a postulate of continuity, and then he doesn't much talk about it, why that would be, because it would be line drawing, just like Leibniz's principle of perfection, gaplessness, leaplessness, jumplessness, perfection of the continuity. And then Brouwer has a different kind of continuity. He makes some model. He's like, well, what if it just kind of clumps and then it divides like a biological cell? It just kind of duplicates, and those duplicate ad infinitum. So when I think of Brouwer's notion of the infinitesimals, it's compared to like Peano's notion of the infinitesimals, Dodgson's notion of the infinitesimals, Cavalieri's notion of the infinitesimals, Xenocrates' notion of the infinitesimals, Price's, Leibniz's, Newton's, fluents, fluxions, Leibniz's differential. These are each kind of different. And then for the real standard mathematical account, it's kind of Cavalieri's, and then for Xenocrates' account of the mathematical infinitesimals is these iota values, because they do add up. That is, after the geometric series, it's other sort of prototype, if kind of half open various ways, to make this measure 1.0 and give a continuous domain for something for the rationals to attain to be. And then for this signal reals, after it bounds, for those to come down from the great account of the perfect reconstruction of a signal, the signal reals, they're kind of continuous domain. So when he's talking about Hilbert and Brouwer, then it's also talking about constructivism and intuitionism. So constructivism is the idea is like, well, we can't just fabricate things out of thin air. We got to start with something. And so that is kind of fabricating things out of thin air. But it's like, we're going to have axioms and just say they are so. We got to have axioms out of thin air. And then we can't have anything else out of thin air. They're just axioms. And then anything constructive has to be derived from that. And then the intuitionist is the usual account is like, well, it's got to go to where it matches. Like this descriptive set theory has got to be about all the objects of geometry and everything that's so about it. And like a circle and space inversion. Like you can map a circle to all the area outside the circle just by writing a function 1 over x and just saying, well, the part between 0 and 1, that inverted goes from 1 to infinity. The regular singular points of the hypergeometric are 0, 1, and infinity. It's like do without infinity, do without 0. That's kind of where differential geometry leads these days with its submersions and immersions, but it's lost and it doesn't have a thing. So constructivism and intuitionism have flipped over a bunch of different times over history, because for something like geometry, when it was given by Euclid's panel as points, lines, planes, and so on, and for example circles, and after the classical constructions, anything can be made by a classical construction. Those objects exist, like the circle. Then it's constructive in those elements, the Pythagorean, to say those exist. And it's intuitionist to say it's like, well, we can make that out of the transcendental points of those things. And just like flipping the Cantorian and the Pythagorean together around, then it's just like flipping constructivism and intuition around. So when they say that, it's like, well, what's intuitionism? It's like, it's a study of Lutwidge-Brouwer's account of infinitesimals or continuity. It's like, well, really, that's kind of as much a constructive account itself. It's just kind of whatever is elementary and fundamental on the one side of this inductive argument, the invincible ignorance of the inductive inference. One of the others, those is constructive, and the other one is intuitionist. Now, another account of why, when trying to make a grounds for something like that, the constructivist, is that proofs by contradiction are not constructivist either, or at least according to some constructivists, they're not constructivist. Proof by contradiction is a lot like the proof by contrapositive, except the contrapositive, you already know that there's a causal relation between P and Q. If P, then Q, the proposition, implies that if not Q, then not P. But in a proof by contradiction, you say it's like, well, start by assuming this and this is so. Well, assume the opposite and show how then that would cause a contradiction. So it can't have been so. And so the account of proofs by contradiction are also considered not constructivist. Except in a very course where it's again, it's kind of fed itself its own line, as it were. And so that makes for why many accounts of whether uncountability in ordinary regular set theory is considered constructive or not, is many constructivists where constructive mathematics are just like expansion and comprehension only, derivations. Give me a schema, I make boilerplate. It's constructivist. Structure, its structure emerges. There's no contradictions in it. Compared to having like a proof by contradiction at all, it's like, well, that's just, there must be a restriction of comprehension, so it automatically invokes that every single time then, in every single relation forever. So it's baggage is kind of the way it is. Point being, though, that the constructivism and intuitionism and constructivism and non-constructivism are various things. One is back and forth, just like, well, this is constructivism, and so that, if true, is just intuitionism. And the other one is like, this is constructivism, and that is like, it's broken, but we have this non-constructivist account of why it's looking at it a particular way, or the restriction of comprehension instead of expansion comprehension. It's not entirely a lost enterprise. And the other, then the rest of the image of the reality, here well-foundedness, for example, can not be broken. But it then gets into all sorts of reasons why classical logic is to exclude that, bring Chrysippus's moods for the modal, so that otherwise the quasi-modal account of material implication, which is C rule 1, oh, by the way, C rule end, either one of which can contradict each other, thus make an overall contradiction and a fallacy, has this so why in the greater account, then we relate things like, well, it's got to relate to the geometric series to have a real analytical character, or it's got to relate to, ultimately, this sweep to have real analytical character, and then it does. And then for the models of ordinals and cardinals and numbering and counting, this deconstructive account, to make it so. Then in this monoheno theory of a dually self-infraconsistent, paraconsistent dilithic system, that it's all one theory. And also it's all the usual theories too. All one theory. So let's see. Then now I lost the place here where it was talking about Hilbert and David Hilbert and his mathematical work. He's talking about when Hilbert publishes proof of the existence of a finite ideal basis, Gordon the formalist, or Gordin, that time looked upon as the king of invariants, cried out, "This is not mathematics, it is theology." Hilbert remonstrated then, as he did all his life, against the disparagement of existential arguments as theology. But we see how by digging deeper, he was able to meet Gordin's constructive demands. So here that's just an example. It's like, well, if you can, you can use the tools of an inductive account to make any other. By combining the Null-Stellensatz with the Cayley process, he further showed that every invariant J is an integral algebraic, in emphasis the authors, though not an integral rational, emphasis the author, function J1 ... J mu satisfying an equation, a formula with terms on the left and terms on the right, and then the mixed terms in the middle equals 0. In which the g's are polynomials of the j1 through the j mu. Hence, it must be possible by suitable algebraic extensions to pass from j1 to j mu to a full integrity basis. So algebraic extensions are a bit beyond rational extensions, because the questions about the rationals and is with regards to algebraic is that there are algebraic roots that are not rational roots, like the square root of 2. And so here to say is like, well, we if we take an infinite series of those, then we can get them back to somehow like that the a priori numbers or the accounts of an infinite expression all in non-rationals can result a rational number. That's pretty much contrived and demands its own sort of superclassical reasoning to bridge that gap. There's no way to go from an inductive account to make a closure of an infinitary expression unless there's some kind of result that gives for it why it would be so. And it's not just wishful thinking. And here, for example, Hilbert's account is you could dispatch it by saying it's like, well, now you just added another axiom for that, and you have to defend that. This speaks to kind of the recent talk there was here about the rational algebras, because there are accounts given of things like rational algebras. Like for example, one of the recent stories in the world was, somebody came up with a solution and they've shown the Riemann hypothesis is so. It's like, oh really? How did they do that? It's like, well, they gave an account of these kind of the completions. It's like, well, obviously, if this is rational, I can, and this is rational, then they're both rational. It's like, well, yeah, but this rational and that rational are separated by an arbitrarily irrational thing. And so adding those back up together does not make a line. Kind of like if you have two lattices superimposed at an arbitrary angle, which may be irrational, you can't superimpose them so you can't tell the difference unless you also have the account of the transcendental that makes out of that infinitary completion rational. So the rational algebras sort of takes something like the Riemann hypothesis and it's like, well, it's found a solution. It's like, yeah, well, it found one, now it's not. Welcome to Erdős's giant monster independence. He just shredded it. And now you're welcome to paste it back together and use it as a good example of something that, under the further constraints of where it is so, maybe so. But by itself, it's just another account of a little bit of the leap before you look type of a thing, which, it's really easy then also to write computer programs to do that at lightning speed and these kinds of things. We didn't have calculators in math class, but we did have a compass and an edge. In the construction of his models, Hilbert displays an amazing wealth of invention. Most interesting examples seem to be the one by which he shows that Desargues' theorem. So this is like hundreds and hundreds of years. Desargues is really pretty fundamental, and I need to learn a little bit more about Desargues, D-E-S-A-R-G-U-E, Desargues, because it's kind of after Nicomachus and addition formula and these kinds of things. So he's got some identities and addition formulas. And then similarly to de Moivre about like, hey, sine squared theta plus cosine squared theta equals 1. So all the stuff that came out of that to make the Eulerian and Gaussian complex analysis. Desargues is important in that as well. He shows that Desargues' theorem does not follow from the plane incidence axioms, but that the plane incidence axioms combined with Desargues' theorem enable one to embed the plane in a higher dimensional space in which all incidence axioms hold. So now the problem with that would be along similarly the lines of why this rational approach has to be thoroughly rational, is that's given itself. It's like another completion result it has to prove and not assume, because there are counterexamples that can be readily given. And then the other example by which he decides whether the Archimedean axiom of continuity is necessary to restore the full congruence axioms after having curtailed them by exclusion of reflections. I'm not sure if this is the exact same thing as the postulate of continuity, and whether the Archimedean axiom of continuity then is already around. Klein's model of non-Euclidean geometry could be interpreted as showing that he who accepts Euclidean geometry with its point lines and so on can, by mere change of nomenclature, also get the non-Euclidean geometry. You can't change the names of numbers. That is their number, and it is their name. Those instead are given as to be, as with regards to the parallel postulate, and also this double angle postulate, two ways for geometry to be super Euclidean. That it's either super Euclidean or it's not a geometry anymore. It could be in part. It could be partial. So yeah, about Brouwer then. So this is about Hilbert and his mathematical work. Hilbert's theory of norm residues. Artin, Haas, Chiavelli, Hilbert. Kummer, Minkowski, Kronecker and Dedekind. After the formal investigations from Cayley and Sylvester to Gordon, Hilbert inaugurated a new epoch on the theory of invariance. Indeed, by discovering new ideas and introducing new powerful methods, he not only brought the subject up to the new level set for algebra by Kronecker and Dedekind, they basically just sat in the middle and pasted it together, but made such a thorough job of it that he all but finished it, at least as far as the full linear group is concerned. With justifiable pride, he concludes his paper, Über die vollen Invariantensystem, on complete systems of invariance, which is kind of what we're talking about here. Is like complete systems of invariance need completions to be complete. With the words, thus I believe the most important goals of the theory of the function fields generated by invariance have been attained, and therewith quits the scene. That's this Nullstellensatz, I guess. This is, as we were just reading about, the Nullstellensatz with the Cayley process about the invariance and the algebraic and the rational. So yeah, this is a very useful to help understand that these were considered the coolest and the top sorts of abstractions in mathematics of the day. And in the relations to Hilbert's problems, Weyl writes that Hilbert's Paris address on mathematical problems quoted above straddles all fields of our science. Trying to unveil what the future would hold in store for us, he posed and discussed 23 unsolved problems, which have indeed, as we can now state in retrospect, played an important role during the following 40-odd years. A mathematician who had solved one of them thereby passed on the honors class of the mathematical community. And here, for example, it's some of these problems are not solvable except by deconstructing them and proving them both ways, and then proving how that's not contradicting all of mathematics. Because otherwise, these accounts, kind of like the story of the formalism of Fourier-style analysis, include extra superclassical results necessary, else it's lacking. They're not just magic. There is no magic that isn't logic. So. That's for the account of the great atlas of mathematical independence these days, and the repleteness for the completeness, the continuity, the infinity. Well, so there's plenty more to read from Weyl here to give a great account of the historiographic and as well the formalism in this setting. Fritz Lennon on superfluids. I'll just look here for some formulas and what we got here. So he quotes Goethe, translated by Hermann Salinger, a brief biography of London. There was a philosophical element in the way in which Fritz London approached the problems of science. Quoting from the In Memoriam by Ernst Moritz Manasse. I do not only think of the fact that his doctoral dissertation had as subject a philosophical theme, was subsequently published in Husserl's Jahrbuch für Philosophie und Phänomenologische Forschung. Neither of his important contributions to the epistemological interpretation of quantum mechanics, even more significant, it seems to me that Fritz London was deeply concerned with the fate of physics as a science. This history of science to him meant more than the progressive accumulation and organization of facts. He was convinced that science had a destiny, this destiny of science, he was constantly preoccupied. He often pondered the question whether the generation which had developed the quantum theory had produced a new kind of intellectual cooperation which was bound to exceed the individual achievements of former generations. It was extremely exciting to hear him analyze those fateful years when, in an unprecedented dialogue, one scientist took up the line of thought where it had been left by another. Fritz London recognized in the phenomenon of such combined efforts a unique chance, yet he also became increasingly concerned about the dangers of a superorganization which might stifle the inventive genius and leave no room for creative initiative. I believe that everyone who came in contact with him was fascinated by his spirituality, the luminosity, and radiance of this ever-active mind. On Fritz London, his closer friends were also charmed by the artistic element. But his greatest charm consists in the combination of his artistic and his philosophical nature. Humaneness. So that's just pointing that he had a philosophy of science, and so he already had an inkling of what he figured to be. Then, as regards of there being one theory and that being stifling, it's like on the other hand, that's the only thing that's not stifling, because otherwise no theory would ever be able to stand alone. And so the idea that there's one true theory, and that being totally different than the usual account of non-idealism, because it is an idealism, has it so that otherwise can always be given as the analytical fact that nothing else is really so. So it's to be read that just because there's one true theory, and we can all, if not having it, still attain to it, and we can relay it formally, and if we're all not just all what it is said to be, but all what it's said to do, it could be one theory. That's not stifling; it's enabling. And then with regards to everybody kind of having creative accounts of that, it's like, well, you got to know your history, and it already has one, and otherwise it's an echo chamber or a flash in the pan, or other accounts of the vain or the futile. Talking about thermodynamics, Bose-Einstein condensate. Einstein remarked that this removal of the last vestige of individuality from the molecules of a species would imply a statistical preference of the molecules for having the same velocity, even if any interaction between them were disregarded. See, the account of having to get to Planck length, Planck time, and other accounts of the measures of Planck regime is that those would just have to be much, much lower and smaller than the accounts otherwise of how velocity is supposed to give electron orbitals and other accounts of the discreteness of quanta. The discrete quanta vis-a-vis here the continuous quanta. And so when things in thermodynamics like the Boltzmann constant and molar gas constant, they're mathematical. That gives an account, kind of the opposite of the superclassical results like the geometric series or this sweep function or Fourier style analysis or other accounts of analytical bridges. The superclassical reasoning has it also all the formalism of physics has many various spots where it's approximations or truncations. So the example here, those are usually given is Hooke's law about a pendulum in a finite or infinite well, because it has cases where that's just given off. And how it's given is like, well, here, make an expression. Compute the series and just chop off and truncate the first term. Call that good to first order. So that begins, or is here is given an account as I've been trying to discover these and the total stack of derivations of physics. Which one of those there are is that there's superclassical results needed to make inductive things like the fundamental theorems of calculus and so on, and analysis. And then there's these truncations which give tractability. It's like, well, I can't really be writing infinite expressions all the time. Can I just have a formula and an addition formula particularly, because all I can do sometimes is addition? Sure. So Hooke's law is, and this is about the time of Newton, and then that would probably be related to Cavendish as well, some of the accounts of the pendular motion and what goes on that. But not so much for the statistical mechanics course as it kind of comes to arrive. Then there's like Clausius and Clapeyron, or Clausius and then Arrhenius, and they give accounts for like the statistical things, like what's the difference between Boyle's gas law and the ideal gas law? It's like, well, one of them is not ideal. And so to make it so, and then it has kind of this account as after Clausius and Arrhenius of kind of a 2/3 bit. It's kind of got a √2.5 thing, and then you have like a 2/3 bit, and then those add together. It's like it stacks and makes a level table. If you have a 3-legged table, it will stand solid even if it's not level. So Hooke's law, and then Clausius and Arrhenius, and these sorts. And then wondering about then where to describe further counts like this, the molar gas constant in Boltzmann, Planck's constants, and the derivations go on the Planck's constants. Of course, E equals mc squared is exactly one of these, because the kinetic energy equation is just like, well, compute the expansion as of the Taylor series according to the powers of the derivative, the infinite series of those for all the higher orders of derivatives. And that's an expression that's true according to this writing in terms of E, energy, and M, mass, and C, the speed of light. And it's this infinite expression. E equals mc squared plus mc to the fourth, a 1/2 mc to the fourth. And otherwise, the rest of the terms of this Taylor expansion. It's like, now just cut that off and say it's the first one. And all we're saying is it's a good first order approximation. So most people don't know, they're like, that E equals mc squared. It has it that its first account from Einstein was that it's not a formula, it's an approximation. It's an expression for an approximation. Now, there are accounts where it's given later, it's like they kind of take special relativity's account. It's like, well, now we got the energy of electron. We'll use that to define the energy of electron, to define the energy of electron, to define the energy of electron. Around and around and around it goes. And then that just gives E equals mc squared. Is that an approximation anymore? It's like, oh, no. It's not. It's just a pure number out of a circular definition. So this is the kind of reductionism and the anti-reductionism involved again. So today we're talking about constructivism and intuitionism and superclassical results and pragmatic truncations, the merely partial accounts. All one theory. So here that's with regards to Fritz London. That's with regards to Planck. And so there's angstroms is like, well, this is a scale where things are still visible. And then Planck is like, well, this is a scale where it's beneath the atom's view of what's visible. And you give that a finite value because otherwise its running constants goes to 0. And here it's talking about Einstein is like, hey, when we start looking at the velocity of things, it's like in the Pauli principle, it's like these particles are none alike. They're all different, but they're all alike. This abstraction reduction associated with the stack of derivations, and then London here is talking about that. At this temperature, ... the mean thermal kinetic energy becomes so small that the mean de Broglie wavelength lambda equals h/p assumes the value of the order of the mean molecular distances. When the temperature is located lower below this critical temperature, T0, the velocity distribution becomes inhomogeneous. A finite fraction of all molecules is assembled in the lowest quantum state of momentum, P equals 0, and accordingly has a macroscopically large de Broglie wavelength, while the rest of the molecules have a velocity distribution similar to that of a gas. The fraction of molecules in the lowest state increases with decreasing temperature until at 0 degrees absolute kelvins, all molecules are assembled in this particular state. This is an example of a gradually progressing condensation with respect to the momentum coordinates, quite comparable to an ordinary condensation, except that ordinarily the space refers to the space coordinates. Here that's about that. In the Planck scale, the measures of mass and length and distance and time start to make a natural sort of, here it's called, for the direct positronic C is that it's like, well, it's got a virtual symmetrical partner antiparticle, the positron and electron usually. It's the direct positronic C everywhere. then here it's like the white holes is like a black hole is a gravitational singularity where all geodesics and paths fall in it to the center. And here it's like, well, this is one where all the different types of dimensions spring out of it everywhere. That's kind of the description of the Dirac positronic sea, an ocean of all this stuff, and an Einstein kind of white hole sea, all this stuff. What Fritz Lendon here is talking about is like that from the outside. Similarly, on the outside of a black hole, it looks like a sphere. But at the horizon, it doesn't look like anything but a wall. It's like a cube, but it's a wall. So this gets into some of these accounts like, well, then I can write in the formalisms and the expressions why it's like a cube on one side, but it's linear on the other side. Kind of inverse square in the middle. That being the usual law of gravity. Here after a potentialistic account of fall gravity. The fraction of molecules. This is an example of a gradually progressing condensation with respect to the momentum coordinates, quite comparable to an ordinary condensation, except that ordinarily the order refers to the space coordinates. Moreover, since for a finite fraction of all molecules the de Broglie wavelength lambda becomes infinite, Bose-Einstein condensation represents a quantum mechanism of macroscopic scale. So it reflects high energy according to energy and configuration of experiment. These things fall out opposite of where they usually would. So London's writing here, and he says, in view of the situation I advanced in 1938, the hypothesis that the strange change of state in liquid helium at 2.19 kelvins, even though it occurs in the liquid and not in the gaseous state, is due to the condensation mechanism of the Bose-Einstein gas. The extension of the ideal gas theory to the liquid state was a somewhat unusual assumption, yet not so unrealistic in helium as it would be in any other liquid. So here it's mostly about the states of matter and the notions of the compressible, incompressible, the fluid and the solid, and then the gaseous is compressible. It was known that in helium, the zero-point motion, zero-point motion also gets involved with, like the Dirac positronic sea. And so this would be like Heisenberg's kind of zero-point motion because it's got momentum and position. Is more important than in all other substances and responsible for the fact that liquid helium has a quite extraordinarily open structure, a molar volume about 3 times as large as would correspond to the gas kinetic diameter of the helium atoms. Under these circumstances, it was not quite unjustified to try the hypothesis that the qualitative features of the condensing Bose-Einstein gas might be preserved in liquid helium. It's kind of like water ice, floats because it's denser than liquid water, or less dense than liquid water. Yet somehow to do that, its conformal arrangement actually expands instead of just shrinks and contracts. Most materials, the solid is denser than the liquid is denser than the gas. Not here though. So water is an example in the middle of these things, that water is special, the universal solvent. These ideas have been pursued with particular success by Tizza, Tizza, who took the two-fluid model so literally as to attribute 2 distinct velocity fields to the 2 fluids. Here, that's called flow and flux. And oftentimes those are given things like its flow is this way, its flux is this way. They're the same thing. But here, flow is one way and flux is its opposite. This assumption provided a simple framework for a qualitative interpretation of many of the paradoxical flow properties of liquid helium, which have been quite unintelligible from the point of view of ordinary hydrodynamics. And here there's also, this happens at various scales, like hydrodynamics and hydrostatics, or various energies and configuration of experiment about the running constants, and then also about various supersymmetries, or the symmetries and the invariants and these sorts of things. So it gratifies me to read this more thoroughly and fully, and since I got this book 10 or 15 years ago, or whenever it was, that it can make a lot more sense now. This cost $8 at the bookstore. but it was real hard to find it. He rejected the Bose-Einstein hypothesis, Landau. So we were talking about Landau and Landau levels and this sort of thing. Landau is also an account of the truncations that necessarily get involved, and especially when truncations and superclassical results have to get added kind of at the same time, and making for them that's why that's only very, very carefully framed in terms of the configuration energy of experiment. When Tisa made this prediction in 1938, the theory was not taken seriously enough to be given an experimental test. However, in 1941 in Moscow, Kapitza, Kapitza, in a series of ingenious experiments, gave a convincing quantitative corroboration of the two-fluid model. Therefore, the model was taken up again and considerably developed by Landau, Landau. Landau. He rejected the Bose-Einstein hypothesis and attempted to put the theory on a different quantum mechanical basis, assuming a peculiar kind of excitation of the liquid, quantized vortices, which he called rotons. So here the rotons would relate to the spiral wave and wave spiral accounts. They give what that would be. At closer inspection, however, the roton theory did not prove to be more rigorous than the Bose-Einstein approach. But that's kind of questionable what more rigorous mathematically means. And hence, a decision between two theories on purely theoretical grounds seems rather difficult. It could be that it's independent of them anyways, different energies and configuration experiment together. So I'm going to be reading the superfluids a bit more. I'm already more than familiar with the levels of infinity and a lot of stuff that goes on that. And then it was well with regards to Weyl on Hilbert, that's something else. Because Weyl talks about mathematics and logic, relativity theories as stimulus in mathematical research, so that'd be related. So I'll keep these together then and read that. Whereas this levels of infinity is kind of like an ordinary account, Fritz London is much more or deemed as more of an extraordinary account. Well, that's the talk for today, dear readers. All we got to really was about a couple books that were already kind of taken off the last deck. Let's see what there's coming up out of this next. This is a book from Max Born, Problems of Atomic Dynamics. So you can imagine, and this is also more about the ideas that O.W. Richardson really gives the great sort of introduction. He's like, well, look, you got two circles and they're superimposed. Now they begin to fall apart, or you have two circles that are just barely touching, and then they begin to fall in. Now you got at least three different things that are supposed to be the same thing, and so that gives an account of like the three constants C: electrostatics, electrodynamics, and light speed. And so this problems of atomic dynamics are similar. It's infinitesimal analysis. So yeah, this is part of this dense box of books in quantum mechanics. Well then, gentle readers, I hope you enjoyed this today. I did. What it was about was, in part, is based about just stating the prominence from here of my own account, because that's the only thing I can really call unified and coherent, and that is put together with all the standard account. Then there was quite a bit about that, and then about all the requirements and desiderata of a theory, and then aspects of reflection on theory. And then reading about Hilbert, and talking about Weyl, and talking about Cantor, and duBois-Reymond, and then also the accounts of all the many recounts and retellings of the objects here. And then kind of ending with that, again, is the same, an account of like problems of atomic dynamics as it's given, and when those are results. So I'll be studying this some more, and then the account is to look for finding the last mathematical constants in physics. And then for the truncating accounts, the approximations, those get buried in the account, like the small angle approximation or linearizations. Linearizations, as they're usually called. It's not linear. We need something rational. Linearize it. Or it's infinite. We need something finite. quantize it. And then renormalize it. Well, it must have been denormalized somehow, right? So those have to be picked out of all the stack and then kind of put around them why and how they are around the thing. And then the superclassical results, then all the accounts that make for completions of superclassical results, they all need their kinds of things too to help hold up, support, and promote the giant atlas of mathematical independence and his cousin, big physics. Good day.